Good morning students, I am M. Venkataya, Assistant Professor in the Department of Mechanical Engineering. Now I am going to teach the subject is thermal and hydro prime movers. So in the previous class what I have discussed is the simple gas turbine power plant, that is the systematic layout of simple gas turbine. So in the previous class we discussed in this topic. Then in today's class is how to discuss the actual cycles, that is actual cycles, analysis of simple cycles and cycles with intercooling, reheating and regeneration. So here the actual cycle we have to see here. This is the actual cycle. So we know that the actual cycle we are discussing in the previous class also, that is the open cycle. Open cycle. Second one is closed cycle. Third one is ideal cycle or isolated cycle. Okay, ideal cycle. So it has here the open cycle, closed cycle, and the ideal cycle. The analysis of simple cycles. So we have these are the analysis of simple cycles like open cycle, closed cycle, then the ideal cycle. So cycles with intercooling. So it has some of the intercooling. So that is the intercooling of open cycle, closed cycle, then the ideal cycle. Okay, then reheating of open cycle as well as the closed cycle, then the ideal cycle. So and the regeneration of open cycle, closed cycle, then ideal cycle. So today I have to discuss about the actual cycles and analysis of simple cycles and the cycles with the intercooling, reheating and regeneration. So in the previous class, so we have to see here. In this, in the previous class, the class continuation, that is the performance test on the gas turbines. Performance test on gas turbines. Okay, so that is the first thing is the pressure ratio. So the pressure ratio, it is the ratio of the cycle's highest pressure to its lowest pressure. So the ratio of the cycle's highest pressure. So highest pressure. So pressure in the form of pascals. Okay. So here the pressure ratio, that is it is the highest pressure to its lowest pressure. So highest to the lowest pressure we can call it as the pressure ratio. Then the work ratio. So the second point is the work ratio. The work ratio of a network output to the total work developed in the turbine. So we have to see this is the ratio of network output to the total work developed in the turbine. So then it's called the work ratio. Then the third point is the air ratio. So air in the form of kgs. So air in the form of kgs, that is one kg of air entering the compressor inlet per unit of cycle net output kg for kilowatts. So kilowatts. We have to observe here the air ratio. So here three types, here pressure ratio and work ratio, after that air ratio. So air ratio we are 1 kg of air entering in the compressor. So inlet per unit of cycle and net output workput. So that is the air ratio. Then the compression efficiency. So this is the fourth point and this one is the fifth point. So the fourth point is compression efficiency. So ratio of work needed for ideal air compressor through a given pressure range to the to work actually used by the compressor. Okay. So see here the ratio of work needed for ideal air compressor through a given pressure range to work actually used by the compressor. So that is the main function of the compression efficiency. Then the engine efficiency, that is the fifth point, the engine efficiency. So the engine performance evaluation we have to find here only. Not only here, that is the IC engines also we are performing the enhancement of engine performance of the IC engines as well as the steam turbines also we are discussing from second unit. Now this is the third unit, that is the gas turbine are also we are discussing. So that is the engine performance or engine efficiency. That engine efficiency, it is the ratio of the work actually developed by the turbine expanding hot power gases through a given pressure is called the efficiency of engine. So this is the main thing. It is the ratio of the work actually developed by the turbine expanding hot power gases through a given pressure is called the engine performance or engine efficiency. Okay, next, this is the sixth point, that is the mission efficiency. So in the previous engine efficiency, now that is the engine efficiency. So collective terms of engine efficiency and compressor efficiency of turbine and compressor. So then the combustion, so we have to see this is the mission efficiency. The mission efficiency, collective terms of engine efficiency and compressor efficiency of turbine and the compression, as well as the turbine we have to turbine efficiency and the turbine efficiency of the compressor efficiency, both are together in the mission efficiency. So then the seventh point, that is the combustion efficiency. So the combustion efficiency, it is the ratio of heat actually released by 1 gram of the fuel to heat that would be released by the complete perfect combustion. So this is the combination of combustion efficiency. It is the ratio. So it is the ratio of heat actually released by the 1 kg or 1 gram of the fuel to that heat that would be released by the complete performance combination. So combustion, this is the main thing here, the main thing of the combustion. And then go for the next slide, that is the last efficiency, that is the eighth point is thermal efficiency. So we should understand this thermal efficiency and each and every, that is the IC engines and the steam turbine. Now the gas turbine also we are discussing here we are discussing the thermal efficiency. So the thermal efficiency, it is the percentage of total energy input appearing as network output of the cycle. So net work output of the cycle. This is the thermal efficiency. Thermal efficiency. So once again we have to see it is the percentage of total energy output appearing as network output of the cycle. So once again I repeated the terms of terminology, that is performance test. So we have to see here this is the pressure ratio, first of all, pressure ratio and the work ratio, then the air ratio. After completion of this is the first one and the second one, this is the third one. Then go for the fourth one is compression efficiency, then engine efficiency. After that mission efficiency, then the combustion efficiency. After that last that is the thermal efficiency. Okay, so this is the performance test on the gas turbines. Okay, then so different types of gas turbines power plants will be there. that is the gas turbine power plants can be classified mainly into two categories. So that is what are that two categories is open cycle gas turbine power plant and the closed cycle gas turbine power plant. So we have to divide it into two types of gas turbines. That two types is open cycle gas turbine and the second one is the closed cycle gas turbine. Okay. So this is the thing. So we have to see the different types of gas turbine power plants. That is the gas turbine power plants can be classified into mainly two types. One is the open cycle gas turbines. That is the open cycle gas turbine power plant and the closed cycle gas turbine power plant. Okay, is it clear? Then, here the first talking about the open cycle gas turbine power plant. In this type of plant, the atmospheric air is charged into the combustion through a compressor and the exhaust of the turbine also discharged to the atmospheric. So first of all, what is meant by atmospheric? So what is meant by atmospheric? Atmospheric pressure is nothing but the surroundings. Surroundings pressure is called the atmospheric pressure. Now in this room we have some of the pressure will be there. That pressure is called the atmospheric pressure. That is the gauge pressure. Absolute pressure is nothing but the atmospheric pressure plus gauge pressure. So that is called the absolute pressure, but we want the atmospheric pressure. The absolute pressure minus gauge pressure is called the atmospheric pressure. Okay. So the open cycle gas turbine, where in this type of plants, the atmospheric air is charged into the combustion through a compressor, and the exhaust of the turbine also discharged to the atmospheric pressure. Atmospheric pressure. This is the main thing of open cycle gas turbine. And coming to the closed cycle gas turbine power plant, in this type of power plant, the mass of the air is constant. So the mass of the air is constant. So the mass of the air is constant, or another stable gas used as a working medium. So another suitable gases used as a working medium. So medium is here another suitable gases are used and circulates through the cycles over and over again. Okay. So here this is the flow diagram of gas turbine power plants. So that the open cycle gas turbine power plant and its characteristics. So we have to see the gas turbine usually operates in an open cycle. So we have to see this is generally the gas turbine usually operates on a open cycle. Okay, open cycle. Air at ambient conditions is drawn into the compressor where its temperature and pressure are raised. So we have to see here. This is the fresh charge. That is fresh air into the compressor. So what is the main function of the compressor? To compress the air plus fuel mixture or air. Which one is inside that is if you take the air compressor, and if you take the gases or oil, whatever it is, but we have the main function of the compressor is to compress the air or liquid. So then it is the 1 to 2 stages. What will happen here is the air compressor. The main function of the compressor is to compress the air. And then it will send to the combustion chamber. So in this combustion chamber, this is the inside the body. So enter into the air plus fuel. So in this combustion chamber, it will be ignited because of this compressor. We compress the air. That air will enter into the combustion chamber. At that time, the fuel also entering. So the fuel plus air will be stay in this combustion chamber. So in this combustion chamber have ignited. Then the power. Here the power will went to turbine. So the turbine. This is the turbine, and this one is the compressor. So this is the turbine have some blades. It when the power will be inside the turbine, the blades are will rotated, and that blades are connected to the shaft. That shaft will be there here. That shaft have top of the in that shaft you have a magnetic field. So the magnetic field, and when the rotates the blades, and the shaft will be moved. Shaft is fastly rotating, speedily rotating. At that time, the power will be produced with the help of magnetic field. So the power will be produced. In this after completion of the gases will send down. This is the process of 3 to 4 process. Okay, this is the working principle of gas turbines. Okay. So that the gas turbines usually operates on open cycle only, and air at ambient conditions is drawn into the compressor where its temperature and the pressure are raised. Okay, and then this is the open cycle gas turbine power plant. The characteristics, some of the important points, that is the high pressure air processed into the combustion chamber. So where the fuel is burned at the constant pressure, burns the gases at constant pressure. Here the burns the gases at constant pressure. Okay. Then the high temperature gases then enter the turbine where they expand it to atmospheric pressure while producing the power output. So while the high temperature gases then enter the turbine, where they expand it to the atmospheric pressure while producing the power output. Okay, and then some of the output power is used to drive the compressor. The exhaust gases leaving the turbines are thrown out, not circulated, causing the cycle to be classified as an open cycle. So we are using basically in this gas turbines. So we are basically what we are using here. The cycle is the open cycle we are using. Okay. In this the ideal cycle that the working fluid undergoes in the closed loop, it's a Brayton cycle. It is made up of four internally reversible processes. So we are using the open cycle. So in this ideal cycle we are using the Brayton cycle. So we are using that Brayton cycle. It is made of four internally reversible processes. So here in this we have to see here, this is the thermal and hydro prime mover. We are discussing about the thermal prime movers. That is the first thing is first IC engines. In these IC engines we are using the Carnot cycle, diesel cycle, and Brayton cycle, like that. And then coming to the steam turbines, in this steam turbine we are using the Rankine cycle, and coming to the gas turbines we are using Brayton cycle, like ideal cycle, open cycle, then the closed cycle. Okay, so in this point of view, in this gas turbine point of view, we are using the Brayton cycle. We have to remember these things. Okay, then so here the gas turbine power plant. So this is the temperature and entropy values diagrams. So this is the A diagram, this is the TS diagram, and the P is the PV diagram. So let's see here. This is the P. TS means temperature and entropy diagram, and this is the pressure and volume diagram. Okay. So we have to see some of the important things. That is the process 1 to 2. That is the 1 to 2 process will be there, and the 2 to 3 process is there, and 3 to 4 process, 4 to 1 process. In this process, we know that we studied in the first unit and second unit also. So that the thing, so 1 to 2 process, isotropic compression. So no change in entropy. So no change in entropy. That process is the isentropic compression. So isentropic compression. Then the 2 to 3 process, that is the 2 to 3 process Q in. So constant pressure heat addition. So constant pressure heat addition. Then the 3 to 4 process isentropic expansion. So 3 to 4 process, that 3 to 4 process isentropic expansion. Then the 4 to 1 constant pressure heat rejection. So 4 to 1, that is the constant pressure. P equal to constant pressure heat rejection. So let's see once again the point 1 to 2 process. The point 1 to 2 process isentropic compression. So isentropic compression will be there in that particular 1 to 2 process. And the 2 to 3 process, that is constant pressure heat addition. Constant pressure heat addition. Heat it will be taken. And then the 3 to 4 process isentropic expansion. So 3 to 4 process isentropic expansion. Then the 4 to 1 process constant pressure. Here also the constant pressure, but the heat is rejection. That process will be seen here. The temperature and the entropy diagrams of an ideal Brayton cycle we are discussing is a Brayton cycle. Brayton cycle, that is the ideal Brayton cycle. Ideal Brayton cycle. Okay. Then, so methods to be improvement of today's class, that is the thermal efficiency of open cycle gas turbine. So we have 3 types of things is there. That is one thing is intercooling, second one is reheating, third one is regeneration. So this is the thing. So that is the intercooling and reheating, regeneration. In this the 3 topics will be there here. Then today's class is what I have discussed is the first thing is actual cycles, that is ideal cycle. Second one is open cycle. Third one is closed cycle. Then these are all the actual cycles we are discussing, and the engine performance evaluation of gas turbine. So engine performance test. Performance test on gas turbines. Then intercooling, that is intercooling. Reheating, regeneration. Third one is regeneration. So today's classes I have discussed these are the terminology, and then next class I will discuss about the intercooling and the reheating and regeneration. Okay, thank you.